Alright, let's go. Number 10. The orphan galaxies. Every galaxy we have ever studied exists within a context. It belongs to something. It is part of a group, a cluster, a supercluster, embedded in the vast gravitational web that connects matter across the observable universe. The Milky Way belongs to the local group. The local group belongs to the Virgo supercluster. This is how galaxies work. They form together, they grow together, they are bound together by the same gravitational architecture that has structured the cosmos since its earliest moments. Then astronomers started finding galaxies that belong to nothing. Orphan galaxies are fully formed, luminous, chemically complex stellar systems drifting alone through the deepest voids of intergalactic space. No parent cluster. No neighboring galaxies. No gravitational context whatsoever. Just a complete, functioning galaxy suspended in a region of space where nothing else exists for hundreds of millions of light years in every direction. The problem is not just their isolation. The problem is that our models of galaxy formation require a scaffolding of dark matter and gravitational interaction to work. Galaxies do not form in empty space. They form at the intersections of dark matter filaments where gas can accumulate, cool, and collapse into stars. A galaxy forming in a void, in the absence of that scaffolding, should be physically impossible. Several mechanisms have been proposed to explain how a galaxy ends up alone. Gravitational ejection from a cluster during a collision. Tidal stripping that leaves a galaxy's stars behind while its dark matter halo is pulled away. Runaway trajectories from ancient mergers. But none of these explanations account for all the orphan systems we have found. Some of them appear to have formed in isolation, in the void, without the infrastructure our models say is required. What does it mean that the universe is producing galaxies in conditions where galaxies should not be able to form? Every orphan galaxy is a completed structure built from hundreds of billions of stars, drifting alone through a darkness that our physics said should have prevented its existence. Number 9. Ultra-diffuse galaxies. In 2015, astronomers using the Dragonfly telephoto array discovered something that forced an immediate re-examination of what a galaxy actually is. Scattered throughout the Coma cluster, one of the largest galaxy clusters in the nearby universe, were objects the size of the Milky Way containing only 1% of the Milky Way's stars. They were called ultra-diffuse galaxies, and they should not exist. A galaxy the size of the Milky Way, but with almost no stars, is a structural paradox. Normal galaxies of that physical scale contain hundreds of billions of stars. Their gravitational mass, their star formation history, their chemical evolution, all of it scales with their size. An object spanning the same diameter, but containing only a billion stars, is so tenuously held together that the gravitational tides of neighboring galaxies should have torn it apart billions of years ago. But some ultra-diffuse galaxies presented an even more disturbing problem. In 2018, astronomers studying a galaxy designated NGC 1052, DF2, made a measurement that sent a shock through the astrophysics community. They measured the velocities of globular clusters orbiting within the galaxy and found something that violated one of the most fundamental assumptions in modern cosmology. The stars were moving as if there was almost no dark matter present. This was not supposed to be possible. Dark matter is the invisible scaffolding that holds galaxies together. It constitutes the vast majority of a galaxy's total mass. Without it, the visible stars cannot orbit fast enough to remain bound. NGC 1052, DF2 appeared to be a galaxy made almost entirely of ordinary matter, with dark matter conspicuously absent. If dark matter can be separated from a galaxy, if galaxies can exist without it, then dark matter is not the inseparable structural component we believed it to be. And if that assumption is wrong, the foundations of our entire model of cosmic structure formation become uncertain. Ultra-diffuse galaxies are not just strange objects. They are objects that exist in direct contradiction to the framework we use to explain why anything exists where it does. Number 8. The Fermi paradox. The universe is approximately 13.8 billion years old. It contains at least 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. A significant fraction of those stars host planetary systems. Within those systems, planets exist in the habitable zones where liquid water can persist on a surface. The chemistry required for life, carbon, hydrogen, oxygen, nitrogen, is among the most abundant chemistry in the cosmos. The mathematics of probability applied to these numbers produces one overwhelming conclusion. The universe should be saturated with life. Intelligent civilizations should have emerged billions of years before our own. Given sufficient time, even slow expansion at a fraction of the speed of light would allow a civilization to colonize an entire galaxy within a few million years, a negligible fraction of the time available. We should be surrounded by evidence of other civilizations. We should have detected their signals, their megastructures, their modifications to stellar environments, their waste heat, their transmissions. We have detected none of it. In 70 years of increasingly sensitive observation across every wavelength of the electromagnetic spectrum, the universe has returned nothing but silence. This is the Fermi paradox, and no resolution to it is comfortable. If civilizations are rare, it implies that some filter exists in the development of intelligent life, a step so improbable that almost nothing makes it through. The disturbing question is whether that filter lies behind us, in the extraordinary chain of events that produced complex life on Earth, or ahead of us, waiting for every civilization that reaches our level of development. If it lies ahead, then something destroys or silences every sufficiently advanced civilization before it can make itself known. That something could be self-inflicted. It could be environmental. It could be a consequence of the physics of advanced technology itself. The silence of the universe is not neutral data. It is information. And what it may be telling us about our own future is the most unsettling implication in all of science. Number 7. The Great Attractor. In the 1970s and 1980s, astronomers mapping the velocities of galaxies in our local universe encountered a profound anomaly. The Milky Way, the Local Group, the Virgo supercluster, and hundreds of thousands of other galaxies across a region spanning 500 million light-years were all moving in the same direction. Not because of any visible mass, not because of any identified structure. They were being pulled towards something in the direction of the constellation Centaurus that could not be directly observed because it sat behind the obscuring dust and stars of our own galactic plane. They called it the Great Attractor, and it represents a gravitational force so immense that it is drawing millions of galaxies toward it at speeds of up to 600 kilometers per second. For decades, the Great Attractor remained one of the most disturbing mysteries in observational cosmology. When X-ray and radio telescopes capable of piercing the galactic plane were finally able to examine the region directly, they found a massive galaxy cluster, the Norma cluster, which could account for some of the anomalous motion. But not all of it. Further investigation revealed that the Norma cluster was itself falling towards something even larger, a structure called the Shapley supercluster, the most massive concentration of galaxies in the nearby universe, containing the mass of tens of thousands of Milky Ways. But even the Shapley supercluster does not fully account for the observed velocities. We are inside a gravitational drainage system of incomprehensible scale. The Milky Way is falling. Everything around us is falling towards something so massive that we have not yet fully identified it, in a direction we spent decades unable to observe. The universe is not static around us. It is pulling us somewhere, and we are only beginning to understand toward what. Number 6. Fast radio bursts. On July 24, 2001, a radio telescope in Parkes, Australia recorded a burst of radio waves lasting approximately 5 milliseconds. The signal was so bright, so brief, and so energetic that the astronomer who discovered it, Duncan Lorimer, initially suspected an instrument artifact. The burst had traveled across billions of light-years. In less than the time it takes to blink, it released more energy than the sun emits in 3 days. Fast radio bursts are among the most energetic phenomena in the observable universe and among the least understood. Since Lorimer's discovery, hundreds have been catalogued. Some repeat. Most do not. They arrive from all directions across the sky with no obvious pattern. The distances involved are intergalactic. The energy requirements are extreme. The physical mechanism capable of producing a burst this energetic in this short a time is not fully established. Magnetars, the most magnetically intense objects in the known universe, are the leading candidate for at least some fast radio bursts. In 2020, a fast radio burst was detected from a magnetar within our own galaxy, confirming a connection. But the magnetar that produced it was orders of magnitude less energetic than the most powerful extragalactic bursts on record. Some fast radio bursts appear to be repeating with patterns. Periodicities have been detected in certain sources that suggest a physical structure or rotation is involved. In 2022, a fast radio burst was detected with a pattern repeating every 16 days. No magnetar model cleanly explains this periodicity. We are detecting millisecond flashes of energy from across the universe, some of which appear to be structured, patterned, and periodic. We do not know what produces them. We do not know if there are categories of fast radio bursts that require entirely new physics to explain. Every time we point a radio telescope at the sky, more arrive. The universe is transmitting something. We do not yet know how to read it. Number 5. Population 3 stars. Every star you have ever seen is a second-generation object or later. It is built from material that was processed inside a previous star, forged in the nuclear furnace of a stellar predecessor that lived, died, and scattered its contents across space before our star and our planet formed. The Sun contains iron, carbon, oxygen, silicon. None of that was created in the Big Bang. It was manufactured in earlier stars and distributed through supernovae. This means there must have been a first generation. Stars that formed from nothing but the primordial hydrogen and helium produced in the Big Bang itself. Stars with no heavy elements whatsoever. Astronomers call them population 3 stars. And we have never directly observed a single one. Population 3 stars are predicted to have been enormous. Without heavy elements to cool the collapsing gas clouds efficiently, the first stars could only form when their clouds reached much higher temperatures. The result would have been stars hundreds of times the mass of our Sun, burning at extraordinary temperatures, producing intense ultraviolet radiation, and living for only a few million years before exploding in supernovae of a violence we have never witnessed. These explosions seeded the early universe with the first heavy elements. They initiated the chemical enrichment that would eventually make planets, chemistry, and biology possible. Every atom of carbon in your body passed through the interior of a population 3 star. You are made of material that was processed in objects we have never seen. The James Webb Space Telescope is currently searching for population 3 stars in the most distant, earliest galaxies it can observe. Tentative signatures have been detected, but a confirmed direct observation remains elusive. The stars that made everything possible, that built the chemical foundation of the entire observable universe, have so far remained invisible to every instrument we have ever built. Number 4. The lithium problem. 3 minutes after the Big Bang, the universe cooled enough for protons and neutrons to combine into the first atomic nuclei. This process, called Big Bang nucleosynthesis, is one of the most precisely calculated events in all of cosmology. The physics is well understood. The conditions are well constrained. The predicted abundances of hydrogen, helium, and lithium that should have emerged from this period are numbers we can calculate with extraordinary confidence. Hydrogen and helium match. The observed abundances in the oldest stars align with theoretical predictions to within measurement uncertainty. This is one of the great confirmations of the Big Bang model. Lithium does not match. The oldest stars in the universe, population 2 stars with the lowest heavy element content, the closest living proxies we have for the earliest stellar populations, contain approximately 3 times less lithium than Big Bang nucleosynthesis predicts. This is not a small discrepancy. It is not within measurement error. It is a factor of 3, a systematic deficit that appears in every ancient star we have examined across decades of observation. The lithium problem has been known since 1982. It has not been solved. Every proposed resolution creates new problems. If the lithium was destroyed inside the stars themselves, the mechanism for doing so should also destroy other elements in ways we do not observe. If the Big Bang produced less lithium than our models predict, our understanding of conditions during the first 3 minutes is wrong. If new physics beyond the standard model consumed the lithium somehow, we have no confirmed mechanism. The first 3 minutes of the universe produced the wrong amount of a fundamental element. We have known this for over 40 years. The universe's origin story contains a chapter that our best physics cannot yet read. Number 3. The horizon problem. Look at the cosmic microwave background. The oldest light in the universe, the afterglow of the Big Bang, emitted when the cosmos was 380,000 years old. Map it across the entire sky. In every direction, in every region, the temperature is the same to within 1 part in 100,000. The universe is uniform to a precision that defies intuition. Here is why that uniformity is one of the most disturbing facts in cosmology. The regions of the universe we observe in opposite directions of the sky are separated by 93 billion light-years. They have never been in contact. The universe has not existed long enough for light, the fastest possible signal, to have traveled between them. They have had no opportunity to exchange energy, equilibrate temperature, or reach any kind of thermal agreement with each other. Two regions that have never interacted, that have been causally disconnected since before the cosmic microwave background was emitted, are at the same temperature. In physics, thermal equilibrium requires contact. Regions reach the same temperature by exchanging energy. These regions could not have done that. Yet they are identical. The standard resolution to the horizon problem is cosmic inflation, a period of exponential expansion in the universe's first tiny fraction of a second that stretched a small, causally connected region to a size larger than the observable universe. If inflation happened, the uniformity is explained. The regions were in contact before inflation separated them. But inflation raises its own questions. What triggered it? What ended it? What physical field drove it? We have no direct observational confirmation that inflation occurred. We have its predicted consequences, including the uniformity that required an explanation. We are using a theoretical mechanism we cannot directly verify to explain an observation that breaks the physics we can verify. The horizon problem is solved only if inflation is real. And inflation remains one of the most consequential unconfirmed hypotheses in all of science. Number 2. The antimatter asymmetry. When energy converts into matter, it does not produce matter alone. It produces matter and antimatter in equal quantities. This is not a hypothesis. It is one of the most precisely tested symmetries in all of physics. Every particle accelerator ever built confirms it. Every high-energy collision produces pairs. Matter and antimatter emerge together in exact balance. The Big Bang was the most energetic event in the history of the universe. By every law of physics we possess, it should have produced equal quantities of matter and antimatter. Those quantities should have found each other, annihilated completely, and left a universe containing nothing but radiation. We exist. Therefore, something went wrong. Or more precisely, something was asymmetric in a way our physics cannot fully account for. For every billion antimatter particles produced in the Big Bang, there were approximately 1 billion and 1 matter particles. That excess of 1 part per billion survived the annihilation. It became every galaxy, every star, every planet, every atom of every living thing that has ever existed. The entire observable universe is constructed from a rounding error in the symmetry between matter and antimatter. The standard model of particle physics predicts a mechanism for this asymmetry. CP violation, the tendency of certain particle decay processes to behave slightly differently for matter and antimatter. But the CP violation measured in the standard model is orders of magnitude too small to account for the asymmetry we observe. The matter excess that produced the universe is larger than our best physics can explain. Something in the first moments of the universe violated matter-antimatter symmetry at a scale we cannot reproduce, cannot directly observe, and cannot currently explain. The reason you exist, the reason anything physical exists, is an asymmetry embedded in the origin of the cosmos that remains one of the deepest unsolved problems in all of science. Number 1. The Hubble tension. Edwin Hubble measured the expansion rate of the universe in 1929. Since then, measuring that rate precisely has been one of the central projects of cosmology. The number that describes how fast the universe is expanding is called the Hubble constant. Getting it right matters enormously. It tells us the age of the universe, its size, its ultimate fate. Everything in cosmology depends on it. For decades, two independent methods of measuring the Hubble constant returned values that did not agree. And the disagreement has not gone away. It has grown more precise, more confirmed. and more alarming. The first method measures the cosmic microwave background, the oldest light in the universe, and uses our best model of early universe physics to calculate what the expansion rate should be today. This method returns a value of approximately 67 kilometers per second per megaparsec. The second method uses distance ladders, Cepheid variable stars, and type Ia supernovae to measure the expansion rate directly from observations of the nearby universe. This method, refined over decades by teams including the SH0ES collaboration, consistently returns a value of approximately 73 kilometers per second per megaparsec. These two numbers should be the same. They are measuring the same universe. They disagree by approximately 9%, and the statistical confidence of the disagreement has now exceeded 5 sigma, the threshold physicists use to claim a discovery. This is not measurement error. Both measurements have been checked, rechecked, and independently confirmed. They are both correct, and they contradict each other. The Hubble tension means one of two things. Either our model of early universe physics is wrong, and the cosmic microwave background is not telling us what we think it is, or our understanding of the nearby universe is wrong, and the distance ladder contains a systematic error that has survived decades of independent verification. Either conclusion would require a fundamental revision of cosmology. A third possibility is more disturbing than either. Perhaps both measurements are correct and the universe itself changed. Perhaps the expansion rate in the early universe genuinely differs from the expansion rate today in a way that requires new physics. Dark energy that evolves over time. A new particle species that existed in the early universe and has since decayed. A modification to general relativity that operates differently at different cosmic epochs. We are measuring the same universe twice with our best instruments and getting different answers. The cosmos is telling us something about itself that our current physics cannot hear. And until we can resolve why two precise, confirmed, independent measurements of the universe's most fundamental parameter disagree, we cannot claim to understand the universe we live in. Like the video and subscribe to support our channel, and we will keep making more videos like this for you.